This is a podcast that summarizes and explains how to proceed when one wants to do a chi-square test. This is sort of a recipe. Be aware that chi-square usually is written in Greek letters, and this is the letter chi, so what you typically see is chi-square test. Our recipe consists of 7 steps. The first step, we formulate our null hypothesis. This null hypothesis typically aims at saying that there are no associations. Let us formulate something here. I will have data with eye colors and hair colors, and I would say here, in case as an example, no associations between hair and eye colors. So this is our null hypothesis, and we want to typically disprove this one. What we do to disprove a null hypothesis, so the first thing is, number 2, we put our data into Excel and create a nice bar chart to have an optical impression of the data. Then in the third step, we add row and column totals and the number of samples n. Then we create a table of expected frequencies. Then we compute the chi-square. In the fifth step, check the table, meaning that you compute these degrees of freedom, and the chi-square is computed with this formula. We will see in Excel how it is implemented. Then step number 6, we could also directly compute the p-value of the chi-square test with Excel. And to finish, it is usually useful to compute some of the association measures, be it the Kramer's V or the corrected contingency measure. You see they are almost the same. The difference is that here in the denominator you have this chi-square plus n, and here you multiply it again with this minimum of row and column numbers. Alright, then let's start with putting the data into Excel. I have already done that here. We see here measured data. We arranged it such that the hair color is in the rows and the eye color is in the other way around. The hair color is in the rows, right? Each row is one hair color, and each row here is a eye color. Column, row. So I say it once again, thinking that I again mixed it up. So each column is a hair color and each row is an eye color. And we have here 23 of our participants that were blonde and had blue eyes. Or for example here we had 12 participants with black hair and brown eyes. We can create a bar chart with Excel very easily. So let's see, let's maybe reproduce this one. So it is insert, German einfügen. Then you can go here, Säule or column, and you can just choose the very first one. But before you have to mark the area here. So let's choose the very first one. And this is what's being produced. So typically the colors are not yet fine here. So that's why we can choose them. Here, for example, first one, right click, format data, and then you go to filling, you say one colored filling, and you choose your appropriate color. Here maybe a little bit of a brighter blue. Right? So this is how you create this nice bar plot. This is always a good idea because then you see what your data looks like. Good, that was the first step. Now let's see what the next step is. Next step, we add row, column totals and the frequency n. Let's do that. So we sum here. This is the total of the rows. So we write sum or Summe, if you have a German speaking machine, of B3 till B6. And we copy paste that till here. Now we have to move our diagram a little bit. Then we have here the column sums, or the sum over all columns, is equals to Summe or sum of B3 till F3. Copy paste it down, and you can also copy paste to here, because this in the box here is the total number of samples. So let's make that optically a little bit more appealing by putting some frame, and also here putting some frame. So that's the total number of samples. That should also be the same if we do the total column sums. So that is sum of G3 till G6. That should also yield 247, and that's fine. Good. So what's the next step? We have done the third step here. Now we do the fourth step. We create a table of expected frequencies. So the expected frequencies, how are they computed? Expected frequencies are computed according to ratios of the total sum of the rows. Here, for example, 38 compared to the total number of samples. So we would expect that in the orange box, for example here, dancing with food, we would have the ratio of the total number of cats here, in that case, that were given food, compared to the total number of cats participating in the experiment, multiplied, of course, by the number of cats, green, that were actually dancing. Right, so the yellow thing is under here. And we would expect that we could reproduce here the stuff up here if there were no associations. That's how we compute these expected frequencies. So now let's do that in Excel. So here we make another table, expected frequencies. And now what do we have to do? So we have to take, let's start with the field up there. So what we do to reproduce this in terms of what it would be like if there would just be expected frequencies. So this is the ratio of the field in B7 and divided by the field G7, which is the number of total samples, and I multiply this with the field G3, which is the measured the total samples that have here blue eyes. Now I have to think, if I would like to do copy paste, what has to stay fixed and what has to adapt. So what has to stay fixed is in the B7 field, that's the green field, there you should keep the 7 fixed. So you put the dollar, because it's always in the 7th row in Excel. Then in the field G7, that's the violet blue field, that's the 247, everything should be fixed because that's always the same field. And then in the field G3, that's the blue field, what remains fixed, that's the column G that remains fixed, but the row index will change. So I put the dollar here and press enter. Now I can do copy paste. I have 5 columns and 4 rows. Insert everything and I have the expected frequencies. So then let's undo the color here. Good. Now what's next? Now we can compute the chi-square. For that we first identify R and C ideally, and then proceed according to the formula given here. So R, let's just put it, number of rows is equal to 4, and C, number of columns, is equal to 5, just for later use. Now let's create the table for the chi-square computation. Let me put these things a bit outside. Let's put them here. If we do this computation manually, then we can now write here equal to, what do I have to take? I have to take the fields in the expected frequencies and in the measured, and I have to subtract them, square them and divide them. So this is equal to B12 minus B3, that whole thing squared, so the order actually doesn't matter, you can bring B12 before B3 or the other way around, and I divide this by the expected frequency B12. I do again copy paste, insert everything, and for the chi-squared I sum up and I get equal to sum of the B18 till F21. That's the chi-square that I get. Measure value of 68.98. Now with this chi-square I can go into the table. I compute df, the degrees of freedom, that is r minus 1 times c minus 1 as a formula, so this is equal to 3 times 4 equal to 12, so I have 12 degrees of freedom. I have my table and I check with degrees of freedom 12. I have the value of 68 for chi-square, and if I check in my table I see that this is highly significant, so that table gives that the p-value is less than 0.1%. I could also directly do this with Excel. By just using the command q.test if you have a German speaking computer, and I just compare the measured frequencies with the expected frequencies. So I have B3 till f6, first argument. Second argument is the expected frequencies, that is B12 till f15. I press enter, and that's the p-value I get. So again here, highly significant associations that I can deduce from that. Alright, so far so good. Now what's next? What have we done? We have done step number 5 and also step number 6. Now we would like to compute some of the association measures, Kramers V, and the corrected contingency coefficient. And to compute these measures we go back to Excel. So let's compute them maybe down here. So here we have Kramer V, and that thing was equal to the Wurzel if you have a German speaking computer, or root if you have an English one. And what we need is the chi-square value. So we make big brackets. Then we put the chi-square value, which we find in the field H23. And we divide this by, let's make another big brackets. We divide this by the number of samples, which is in G7, times bracket the minimum of R and C, which is 4 and 5, and subtract from this minimum 1, close that bracket. Then we close the G7 bracket here for the denominator, and we close the total bracket for the root. And with that we should get the Kramers V of 0.305. So there is association. This is a value between 0 and 1, as we have learned in the lecture. It's not extremely strong, but there is. Let's check with the corrected contingency coefficient. See what this one yields. So here the formula is, we have equal to the square root or Wurzel of, again, the chi-square value, which I find in H23. This time I have to multiply it with the minimum of, again, 4 and 5. And I divide that by big brackets the chi-square value again, which is in H23. Another brackets around it, and add the sample number, which is in G7, which is multiplied with the minimum of 4 and 5 minus 1. So now let's see that we have all the brackets correctly. So this is the bracket for the denominator, that means we still need a bracket for the square root, and we press enter. Now let's shortly check. I think, yeah, this was both correct. Now we get a correlation contingency, a corrected contingency measure of 0.545395, which is higher than Kramers V. That can be, there is no direct connection between these two measures. They should yield comparable results, but that's not always guaranteed. So in this case we have an association which is clearly significant due to the p-value of the chi-square test, which we directly find here, or we read from the table, but the strength of association is not extremely strong. This could be due to the fact that if we look here at the diagram, that we have in the case of blonde hair, a very big peak in the blue-eyed people. On the other side, in the case of red hair, in the last column, we have a very low peak of black-eyed people. So, but this is the other ones look more or less similar. Although 3 columns in the middle, they could be comparable. So maybe this is a reason why there is not such a strong Kramers V or corrected contingency measure. But this is always a question of interpretation, and after all, both Kramers V and the corrected contingency are just numbers that may not be trusted as much as your visual inspection of the data.